There is a place in the universe where you could travel for 330 million light-years in a straight line and encounter almost nothing. Not a star, not a planet, not a cloud of gas. Just an almost perfect, almost infinite expanse of empty space that stretches so far beyond your comprehension that if you tried to visualize it, the image would break your brain before it ever resolved into meaning. That place is real. Astronomers have a name for it. They call it the Buddha's Void. And the moment they found it, they went quiet for a very long time. It was 1981. A team of astronomers led by Robert Kirshner at the Harvard-Smithsonian Center for Astrophysics was conducting a routine survey of galaxy redshifts. This was standard work, the kind of painstaking celestial cartography that fills careers without producing headlines. You point a telescope, you measure how fast a galaxy is moving away from you, and from that you infer its distance. You do it for galaxy after galaxy after galaxy, and slowly you build up a three-dimensional map of your cosmic neighborhood. Nothing glamorous, just numbers and coordinates, and decades of patience. Then the team aimed their telescopes at a patch of sky in the direction of the constellation Bootes, the herdsman, and something went wrong. Or rather, something went impossibly, terrifyingly right. They expected to find galaxies. That is what every patch of sky yields when you look hard enough. Galaxies everywhere, clustered and tangled and streaming along filaments of dark matter that thread through the cosmos like the nervous system of something incomprehensibly vast. But in Bootes, in a region roughly 330 million light-years across, they found almost nothing. In an area of space that should have contained thousands of galaxies by every statistical expectation, they found a handful. The map they were drawing had a hole in it. Not a small hole. Not a gap that could be explained by bad data or a cloudy night. A hole the size of a wound in the universe, gaping and silent, and absolutely real. Kirshner's team initially thought they had made a mistake. They rechecked the data. They repointed the telescopes. They ran the statistics again and again, and each time the answer came back the same. The void was real. It was roughly 330 million light-years in diameter. Roughly 1% of the diameter of the entire observable universe. In terms of volume, if you took our entire Milky Way galaxy and used it as a measuring unit, you would need to stack hundreds of billions of Milky Ways end to end just across this one empty region of space. What they had found was the largest known structure in the universe at the time of its discovery. And its defining characteristic was the near-total absence of everything. The question that burned through the astrophysics community in the months and years after the discovery was simple to ask and nearly impossible to answer. How does something like that exist? How does the universe produce a whole that large? In a cosmos that is supposed to be roughly uniform on the larger scales, filled everywhere with a fine grain of galaxies and clusters and superclusters. How does one region become so catastrophically empty that it makes the surrounding universe look dense by comparison? The answer to that question would take decades to fully develop, and when it did, it turned out to be far stranger and far more personal than anyone initially imagined, because it turned out that we ourselves live inside one. To understand what a void actually is, you have to go back to the very beginning. Not a metaphorical beginning, the literal beginning. The first fraction of a second after the Big Bang, when the universe was not a collection of galaxies or even a collection of atoms, but a seething, roiling plasma of energy so hot and dense that the very concept of empty space had no meaning. In that primordial state, quantum mechanics did what quantum mechanics always does. It introduced tiny fluctuations, random subatomic variations in density that were so small they would have been invisible to any conceivable instrument. But those variations were real, and in a universe that was expanding and cooling at an extraordinary rate, those tiny fluctuations were the seeds of everything that would ever exist. As the universe expanded, gravity did its work. The slightly denser regions, the places where quantum chance had packed fractionally more energy, began to gravitationally attract material from their surroundings. Over millions of years, then hundreds of millions of years, then billions of years, this process amplified. The denser regions became denser still. They pulled in gas. The gas collapsed into stars. Stars formed galaxies. Galaxies clustered together, drawn by mutual gravity along invisible filaments of dark matter that spanned hundreds of millions of light-years. And in between those filaments, in the spaces between the clusters and superclusters, something else happened. The slightly less dense regions, the places where quantum chance had packed fractionally less energy, lost material to their denser neighbours. They became less dense, and then less dense still, and over cosmic time they became what we now call voids. A void is not a mistake. A void is not an absence. A void is the inevitable outcome of the same gravitational processes that built every galaxy you have ever seen in any photograph from any telescope. The universe grew its great structures by draining the spaces between them. Every filament of the cosmic web, every cluster of galaxies, every supercluster stretching across hundreds of millions of light-years, was built using material that was once distributed more evenly and was pulled over billions of years into these concentrated nodes of cosmic architecture. The voids are the holes left behind. They are the negative space of the universe's greatest artwork. And the Bota's void is, by every measure we have, one of the most extreme examples of this process anywhere within the observable universe. But here is where the story starts to accelerate, because the Bota's void, as enormous and as empty as it is, turns out not to be unique. As telescopes improved and surveys grew more comprehensive, throughout the 1980s and 90s and into the 2000s, astronomers discovered that the universe is absolutely riddled with voids. Not just big voids, but supervoids. Structures that make Botas look almost modest. And not just supervoids, but a whole hierarchical architecture of emptiness that mirrors and complements the hierarchical architecture of the matter that surrounds it. The cosmic web, that famous image of filaments and nodes and sheets of galaxies, is only half the picture. The other half is the void network that fills all the spaces in between, a network that makes up roughly 80% of the total volume of the observable universe. Think about that number. 80%. 4/5 of all the space you could theoretically travel through is void. The galaxies, the stars, the planets, the gas clouds, the dark matter halos. Everything that astronomers have catalogued and named and studied for centuries, all of it fits into the remaining 20% of cosmic volume. The universe is, by volume, mostly nothing, and not just a little bit mostly nothing. overwhelmingly, fundamentally, almost incomprehensibly, mostly nothing. When you look up at the night sky and see the Milky Way arcing overhead, you are seeing the densest concentration of matter you will ever have access to. Step outside that band of light, and you step into a universe that is, at its core, built from emptiness. The discovery of just how pervasive the void network is completely transformed our understanding of large-scale cosmic structure. In 1989, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics published their landmark map of the nearby universe, known as the Center for Astrophysics Redshift Survey. What that map showed was something nobody had predicted. The galaxies were not scattered randomly through space. They were not even clustered randomly. They were arranged in sheets and filaments, like the surface of soap bubbles, and between the bubbles were enormous empty regions, voids, with the galaxies concentrated along the thin walls where the bubbles met. The universe looked like a foam, a cosmic foam made of galaxies on the outside and nothing on the inside. That map changed everything. It was the first time anyone had seen the cosmic web in its full, unmistakable, three-dimensional glory, and the visual impact was immediate and visceral. Here was the universe as it actually was, not a uniform sea of galaxies, but an intricate structured network of filaments and voids that extended in every direction as far as the survey could reach. The implication was clear. Voids are not anomalies. They are the fundamental unit of cosmic architecture. They are as important to the structure of the universe as the galaxies themselves. And studying them, understanding how they form and evolve, would be essential to understanding how the universe works. As the surveys grew larger and deeper through the 1990s, the picture of the void network became more refined and more astonishing. The Sloan Digital Sky Survey, which began operating in 2000, eventually mapped the positions of more than 1 million galaxies across more than a quarter of the entire sky. The resulting map was the most detailed three-dimensional portrait of the universe ever constructed, and it revealed a void network of breathtaking complexity. Voids nested inside larger voids. Small voids merged over time into bigger voids. The biggest voids, the supervoids, spanned hundreds of millions of light years and contained almost no galaxies at all. And threading through all of it, connecting the voids to the filaments and clusters and superclusters, was the intricate architecture of the cosmic web. But the survey also revealed something that should have been obvious in retrospect, but still managed to be surprising. The Milky Way itself, along with the Andromeda Galaxy and the entire local group of roughly 50 galaxies that we call home, sits inside a void. Not a supervoid on the scale of Boötes, but still an underdense region that is measurably emptier than the cosmic average. This region is known as the local void, and it extends roughly 150 million light-years in one direction from our position. We live not at the center of cosmic density, but at the outskirts of it, in a relative backwater of the universe, and the emptiness of the local void has been slowly pushing us, along with the rest of the local group, toward the denser regions of the cosmic web for billions of years. The local void is part of the reason that the Milky Way is moving the way it is. In the 1980s, the same year that Kirshner's team discovered the Booter's Void, another group of astronomers discovered that the Milky Way and hundreds of other galaxies in our region of the universe are all streaming in the same direction at hundreds of kilometers per second. This motion, which came to be known as the Great Attractor Flow, was initially attributed entirely to gravitational pull from a massive concentration of matter in the direction of the constellation Centaurus. And there is such a concentration. A supercluster of galaxies called the Hydra Centaurus supercluster that is genuinely pulling us toward it. But more recent measurements have shown that the story is more complicated. Part of what is driving the motion of the Milky Way is not just a pull, but a push. The local void sitting behind us and to one side is emptier than the surrounding cosmic average, and that emptiness creates a relative gravitational deficit, a region of lower gravitational pull that effectively pushes everything near it away, toward the denser, more gravitationally active regions of the universe. The void is not just a hole, it is an engine. This insight that voids actively push galaxies rather than just passively failing to attract them was one of the more counterintuitive revelations to come out of large-scale structure research in the early 2000s. We tend to think of gravity as a force that pulls things together. But in a universe with a non-uniform distribution of matter, gravitational forces act in all directions simultaneously, and the net result depends on the relative density of everything around you. A void, by being emptier than the average, exerts less gravitational pull on its neighbours than the average cosmic background does. The result is that matter near the edge of a void experiences a net force directed away from the void, toward the denser regions outside it. The void effectively repels, not through any exotic force or mysterious mechanism, but simply through the absence of the attractive force that everywhere else is pulling things inward. This is the mechanism by which voids grow. A void starts as a slightly underdense region. The galaxies at its edges are pulled away from it by the denser regions outside, and the void expands. As it expands, it becomes emptier still. The emptier it becomes, the more strongly the surrounding denser regions pull material away from its edges. The process is self-reinforcing. Voids grow, and as they grow, they drive the surrounding matter into the filaments and walls and clusters of the cosmic web. Voids and the cosmic web are not separate structures. They are two aspects of the same gravitational process, evolving together over the entire history of the universe, shaping each other, driving each other, building the large-scale structure of the cosmos from the inside out. And then, in 1998, everything got more complicated. Two independent teams of astronomers studying the brightness of distant supernovae made a discovery that turned cosmology on its head. They found that the expansion of the universe is not slowing down, as gravity should have made it do. It is speeding up. The universe is expanding faster today than it was 1 billion years ago, and faster 1 billion years ago than it was 1 billion years before that. Something is driving the expansion, pushing space apart at an accelerating rate. That something has been named dark energy, and it constitutes roughly 68% of the total energy content of the universe. We have no idea what it is. We cannot detect it directly. We can only infer its existence from the fact that the universe is doing something that gravity alone cannot explain. It is one of the deepest unsolved problems in all of physics. Dark energy changes everything about the story of voids, because dark energy is not just a property of matter or of galaxies. It is a property of space itself. It permeates every cubic meter of the universe uniformly and relentlessly, and its effect is to push space apart at a rate that increases over time. In regions of the universe where matter is dense, in clusters and superclusters where gravity is strong, dark energy's effect is partially counteracted by the gravitational pull of all that matter. The galaxies in a dense cluster are bound together by gravity despite dark energy's attempt to push them apart. But in a void, where there is almost no matter and therefore almost no gravitational force to counteract dark energy, the expansion of space is essentially unopposed. Voids expand faster than the rest of the universe. They grow more quickly than gravitational models alone would predict. They are the regions of the cosmos where dark energy's influence is most naked, most visible, most powerful. This makes voids extraordinary scientific instruments. Because the expansion rate of a void is sensitive to the properties of dark energy, careful measurements of void sizes and their evolution over cosmic time can potentially constrain the nature of dark energy in ways that measurements of galaxy clustering alone cannot. The KIDS survey, the Dark Energy Survey, the Euclid satellite, all of these modern cosmological projects include void analysis as a key component of their scientific programs. By measuring how fast voids grow, how their shapes change over time, and how their abundance depends on cosmic epoch, astronomers hope to narrow down the list of possible explanations for what dark energy actually is. The void is not just an interesting curiosity, it is a laboratory. And dark energy has been running experiments in it for 13.8 billion years. But there is another void that demands attention, not because of its size or its emptiness, but because of where it sits in the cosmic microwave background. The cosmic microwave background is the oldest light in the universe, the thermal afterglow of the Big Bang itself, released about 380,000 years after the universe formed and stretched by cosmic expansion into microwave frequencies. It is almost perfectly uniform, the same temperature in every direction to 1 part in 100,000. But it is not quite perfectly uniform. There are tiny fluctuations, slightly hotter spots and slightly cooler spots that correspond to the density variations in the early universe that eventually grew into the cosmic web. Every galaxy, every filament, every void we see today was encoded in those tiny fluctuations in the cosmic microwave background. In 2004, a team of astronomers using the WMAP satellite discovered an anomaly in the cosmic microwave background that has never been fully explained. In the southern sky, in the constellation Eridanus, there is a cold spot, a region of the CMB that is significantly cooler than the surrounding background. The cold spot is large, roughly 1.8 billion light-years across, and it is too cold to be easily explained by random statistical fluctuation. The probability of such a cold spot arising by chance, given what we know about the statistics of CMB temperature fluctuations, is somewhere between 1 in 100 and 1 in 1,000. depending on exactly how you define the boundaries of the anomaly. It is not impossible, but it is uncomfortable. Several explanations have been proposed for the cold spot. One of the more intriguing is that it corresponds to a supervoid, a region of space so large and so empty that photons of CMB radiation travelling through it lose energy by the integrated Sachs-Wolf effect. This is a real physical process. When a photon enters a void, it falls into a slightly shallower gravitational well. If the void is in a universe with a cosmological constant, as ours appears to be, the void actually expands slightly while the photon is crossing it, which means the gravitational well is even shallower when the photon exits. The net result is that the photon exits the void with slightly less energy than it entered with, and therefore at a slightly cooler temperature. A large enough supervoid in the right location could, in principle, produce a cold spot in the CMB exactly like the one observed. In 2015, a team led by Istvan Sapudi at the University of Hawaii announced that they had found just such a supervoid. Using data from the Pan-STARRS telescope and the Wide Field Survey telescope, they identified an underdense region in the direction of the CMB cold spot, a supervoid roughly 1.8 billion light-years across, with roughly 30% fewer galaxies than the cosmic average. The alignment between the supervoid and the cold spot was striking, and the team argued that the integrated Sachs-Wolf effect from this supervoid could explain a significant fraction of the cold spot's anomalous temperature. Other researchers pushed back, arguing that a void of this size could explain only part of the temperature depression, and that the cold spot remains partially unexplained. The debate is ongoing. But what is clear is that a supervoid of extraordinary scale exists in that region of sky, and that it has measurably imprinted itself on the oldest light in the universe. The KBC void is a different story entirely, and in some ways a more personally unsettling one. In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie, the initials of whose surnames give the void its name, published a paper presenting evidence for an enormous underdense region of space centered roughly on our own position in the universe. The KBC void, as they defined it, is roughly 2 billion light-years across and contains roughly 30% fewer galaxies than the cosmic average within the volume it occupies. It is, by some measures, the largest known void in the universe, and we are, by all available evidence, close to its centre. The existence of the KBC void has significant implications for cosmology, and not all of them are comfortable. One of the most pressing issues in modern cosmology is a disagreement known as the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding, expressed as a velocity per unit distance. There are two main ways to measure it. You can look at the cosmic microwave background, the oldest light in the universe, and use the detailed physics of the early universe to predict what the expansion rate should be today. Or you can measure the expansion rate directly using standard candles like Cepheid variable stars and Type 1a supernovae in the local universe. The problem is that these two methods give different answers. The CMB-based measurement gives a Hubble constant of about 67 km per second per megaparsec. The local measurement gives about 73. the discrepancy is about 8 to 9%, and it is statistically significant, measured at about 5 sigma, which in physics means it is almost certainly not a fluke. The KBC void provides a possible explanation. If we live in the center of a large underdense region, then the local expansion rate of the universe, the rate measured using nearby galaxies and standard candles, would be higher than the global average. This is because the void is less gravitationally bound than the surrounding denser regions, and therefore expands faster. A local expansion rate that is 8 or 9% higher than the global average is exactly what you might expect if you lived near the center of a void as large and as underdense as the KBC void appears to be. The void does not solve the Hubble tension definitively, and many cosmologists argue that the KBC void is not quite large or empty enough to fully account for the discrepancy. But the possibility remains tantalizing. It is possible that one of the most significant unresolved tensions in all of modern cosmology has its origin in the most personal piece of cosmic geography imaginable, the fact that we happen to live in a hole. Living in a void has other consequences that are more subtle but no less interesting. Galaxies that live inside voids are different from galaxies that live in clusters or along filaments. Void galaxies tend to be less massive, bluer, and more gas-rich than their counterparts in denser regions. They form stars at a slower but steadier rate, because they have not been subjected to the violent interactions, mergers, tidal stripping, ram pressure stripping, that are common in the crowded environments of galaxy clusters. A galaxy in a void is in many ways a galaxy left to its own devices. It has not been disturbed by neighbors, has not been stripped of its gas by the hot intracluster medium, has not been tidally deformed by passing companions. It grows slowly and steadily, following its own internal dynamics rather than being shaped by the chaos of its environment. The Milky Way is an interesting case in this regard. By the standards of a galaxy of its mass, the Milky Way is unusually symmetric. It has 2 main spiral arms and a relatively undisturbed disk, without the obvious signs of recent major mergers or violent interactions that characterize many other large spirals. Part of this is probably luck. We've had a relatively quiet merger history compared to many other galaxies. But part of it may also be our location. Living in the relatively underdense environment of the local void and its surroundings has probably protected the Milky Way from the kind of dramatic interactions that galaxies in denser regions experience routinely. Our cosmic address is, in some sense, a quiet suburban neighborhood rather than a cramped urban core. And that relative tranquility may have made a measurable difference to the structure and history of our home galaxy. But the story of voids does not end with their present state. It points forward in time toward a future that is simultaneously fascinating and disturbing. Because dark energy is not static. It is driving the accelerating expansion of the universe, and that expansion is not going to stop. It is going to continue, and according to our best models, it is going to accelerate. And as it accelerates, the universe will change in ways that make the voids of today look modest and temporary by comparison. In the far future, not millions of years from now, but billions and hundreds of billions, the accelerating expansion of the universe will begin to pull apart structures that are currently gravitationally bound. The superclusters of galaxies that line the cosmic web will first stop growing, then begin to dissolve, as the galaxies at their outskirts are gradually stripped away by the expansion. The filaments will thin, the sheets will fade, the void network will grow. Not because voids are forming where there were none before, but because the boundaries between voids and the surrounding structure will blur as matter spreads out into the expanding space. The cosmic web, which took billions of years to build, will slowly disassemble over timescales even longer than those that built it. In the very far future, on timescales measured not in billions but in tens or hundreds of billions of years, the expansion will be so advanced that the local group of galaxies, bound together by mutual gravity, will be the only structure visible in the observable universe. Every other galaxy, every other cluster, every other supercluster will have receded beyond the cosmological horizon, carried away by the accelerating expansion of space to distances from which no light will ever reach us again. The universe, from the perspective of any observer in the local group, will consist of one island of galaxies surrounded by an absolutely infinite, absolutely empty void. No cosmic web, no filaments, no distant galaxies to map. Just the local group, alone in an expanding darkness that will grow emptier with each passing moment, forever. This is not a speculation or a fringe hypothesis. It is the direct prediction of the standard model of cosmology, the lambda CDM model, applied forward in time with the same dark energy that is observationally confirmed to be driving the expansion today. The universe we live in is, on its longest timescales, a universe that is making itself emptier, a universe in the process of erasing its own large-scale structure, a universe building, slowly and inexorably, the ultimate void. Against this backdrop of cosmic-scale emptiness, the question of what is actually inside a void becomes both scientifically important and philosophically charged. Because voids are not, it must be said, truly empty. The Bhuta's void, which contains so few galaxies that its discoverers initially wondered if they had made an error, nonetheless contains some galaxies. Approximately 60 galaxies have been catalogued within its boundaries, scattered like dust motes in an enormous empty room. The void is not a perfect vacuum. It is an extreme underdensity. The difference sounds technical, but it matters enormously because it tells us something fundamental about the physics of void formation and the processes that determine what survives inside them. The galaxies that exist within the Bhuta's void are disproportionately of a particular type. They tend to be spirals, gas-rich, actively star-forming, relatively undisturbed. They are not the red, dead, elliptical galaxies that dominate the densest environments, like the cores of galaxy clusters, where interactions between galaxies are common and gas supplies are frequently stripped away. The void galaxies are blue. They are making new stars. They have had, by cosmic standards, a quiet and productive life. They represent what galaxies look like when you take them out of the environment that most galaxies inhabit and place them in the most isolated conditions the universe can offer. They are nature's experiment in cosmic isolation, and the result is, in many ways, a more pristine version of a galaxy than anything you find in a crowded cosmic neighborhood. The dark matter in voids is also an active area of research. In the standard cosmological model, dark matter is the gravitational scaffolding on which all visible structure is built. In dense regions, filaments, clusters, superclusters, dark matter forms massive halos that anchor the visible matter and prevent it from dispersing into space. But in voids, where the density of everything is much lower, the dark matter halos are smaller, less massive and less concentrated. This has implications for the galaxies that form within them. A less massive dark matter halo means a shallower gravitational potential well, which means the galaxy that forms within it will be smaller, more diffuse, and more vulnerable to disruption by any external force that comes along. Void galaxies, already isolated from the larger cosmic web, are also held together less tightly than their counterparts in denser regions. They are, in every sense, the most fragile structures in the universe. This fragility becomes even more interesting when you consider what dark matter halos in voids might contain beyond the galaxies themselves. In the 1990s, Alan Dressler at the Carnegie Observatories coined the term void phenomenon to describe the apparent absence of faint dwarf galaxies in voids. In denser regions of the universe, dwarf galaxies are everywhere. Tiny, irregular, gas-rich systems that are the most numerous type of galaxy in the cosmos. But in voids, they seem to be underrepresented. The void galaxy population is dominated by larger spirals, with a conspicuous lack of the faint, small systems that would be expected if the void were simply a low-density version of the cosmic average. This discrepancy is still not fully understood. It may reflect the difficulty of forming dwarf galaxies in the weak gravitational potential of a void halo. It may reflect the difficulty of detecting them at the distances involved, or it may reflect something more fundamental about the physics of galaxy formation in extremely underdense environments that our models do not yet fully capture. The search for galaxies in voids has been dramatically aided by the development of blind 21-centimeter radio surveys. The 21-centimeter line is a radio emission from neutral hydrogen, the most abundant element in the universe, and it allows astronomers to detect gas-rich galaxies, even when they're too faint to be seen in optical light. Surveys like the Arecibo Legacy Fast Alpha survey, known as ALFALPHA, have been systematically scanning the sky for 21-centimeter emission, and they have found void galaxies that were previously unknown, faint, gas-rich spirals hiding in the emptiness, too dim to have been catalogued in optical surveys, but still producing enough hydrogen emission to be detected at radio frequencies. These detections have begun to fill in the population of void galaxies in a way that is slowly closing the gap between observation and theory, but significant questions remain about whether the full population has been accounted for. One of the most remarkable developments in void science in recent years has been the development of void-finding algorithms, computational tools that analyze galaxy survey data and automatically identify void regions with well-defined statistical properties. These algorithms vary in their approach. Some look for regions where the galaxy density falls below a certain threshold. Others define voids dynamically as the regions surrounded by matter that is flowing outward. Others use topological methods, analyzing the shape of the cosmic density field to identify the underdense regions as a structural complement to the filaments and nodes of the cosmic web. Each approach yields a slightly different void catalogue, which can make comparisons between different surveys complicated. But the development of robust void-finding algorithms has transformed void cosmology from a descriptive enterprise into a quantitative one, enabling the kind of precise statistical measurements that are needed to constrain the properties of dark energy and test the predictions of cosmological models. The statistical distribution of void sizes, the void size function, is particularly powerful. In any given cosmological model, the void size function has a precise prediction that depends on the values of the cosmological parameters: the matter density, the dark energy density, the equation of state of dark energy, the amplitude of density fluctuations, and so on. By measuring the observed void size function from a large galaxy survey and comparing it to the theoretical prediction, cosmologists can constrain these parameters in a way that is complementary to, and in some cases more powerful than, measurements, based on the power spectrum of galaxy clustering. Voids, it turns out, are particularly sensitive to the equation of state of dark energy, the parameter that describes whether dark energy is a simple cosmological constant or something more complex that evolves over time. Future surveys, like Euclid and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, are expected to dramatically improve our measurements of the void size function, potentially providing the first clear evidence for or against dark energy evolution. But the most emotionally compelling aspect of the story of voids is not the statistics or the cosmological parameters. It is what voids reveal about the nature of the universe we inhabit. We tend to think of the cosmos as a place of stars and galaxies, a place of things. But the void network tells us that the universe is, at its heart, a place of structures defined as much by absence as by presence. The voids are not background noise in the signal of the cosmic web. They are co-equal partners in the architecture of the universe. They shaped the distribution of galaxies. They drove the formation of galaxy clusters. They imprinted their signature on the cosmic microwave background. They push us through space. They may hold the key to understanding dark energy. And they are growing, year by year, billion by year, toward a future in which they will encompass everything that is not gravitationally bound into the most fundamental structure in the late-time universe. There is a concept in astrophysics called the Great Filter, borrowed from discussions of the Fermi paradox, but applicable more broadly. The idea that any sufficiently advanced civilization will eventually encounter a challenge or a transition that either transforms it utterly or ends it. For the universe itself, the void might be that filter. The expansion of the cosmos, driven by dark energy and expressed most purely in the emptiness of voids, is the universe's own great filter, the process by which the intricate, connected, richly structured cosmos of today will eventually transition into the cold, dark, isolated, and essentially void universe of the far future. The cosmic web is not permanent. It is a phase, a beautiful, transient, incomprehensibly complex phase in the life of a universe that began in almost perfect homogeneity, built its structures over billions of years, and will, over timescales that dwarf its current age, return to something closer to what it started as, a universe defined less by what it contains than by what it does not. And yet, within that arc of expansion and dissolution, within the geometry of a universe that is mostly emptiness even now, something extraordinary happened. Matter clumped, stars ignited, planets formed, life arose, consciousness emerged. And somewhere in the KBC void, in a modest spiral galaxy on the edge of a local cluster, a species of terrestrial animals pointed their telescopes at a patch of sky and found a hole 330 million light-years across, and recognized in that void not just an absence, but a structure, not just an emptiness, but a meaning. The void is what the universe mostly is. But we, astonishingly, improbably, are what the universe did instead. The Bota's void continues to expand. At its edges, galaxies stream away from its interior, drawn outward by the gravitational pull of the surrounding cosmic web. Inside it, the handful of galaxies that have remained, those 60 blue spirals, quietly forming stars in the most isolated environment in the observable universe, continue on their own trajectories, indifferent to the vast emptiness around them. They do not know they are inside the largest void we have ever found. They do not know that for 40 years astronomers on a planet in a different part of the universe have been studying them, measuring them, writing papers about them, struggling to understand how they got there and what they can tell us about the nature of space and dark energy and the large-scale structure of the cosmos. They just keep making stars. And somewhere in the cosmic microwave background, in a cold spot in the constellation Eridanus, the afterglow of the Big Bang carries the imprint of a supervoid that formed long before the first stars lit up, long before the first galaxies assembled, long before the cosmic web took the shape we see today. The cold spot is a fossil of emptiness, a record in the oldest light in the universe of the precise region where matter chose, in the first moments of cosmic history, to be slightly less dense than everywhere else. And from that choice, from that quantum fluctuation in the first fractions of a second after the universe began, everything followed. The void formed. The galaxies avoided it. The light cooled as it crossed it. And billions of years later, a satellite called WMAP measured that cooling and flagged it as anomalous, and astronomers spent decades debating what it meant. Because in science, an anomaly is never just an anomaly. It is always an invitation. The invitation the voids extend is a profound one. They ask us to think about the universe not as a collection of objects, but as a field of processes. They ask us to consider what it means for space to be empty, not philosophically empty in the way that troubled the ancient Greeks, but measurably, cosmologically, statistically empty, in a way that has real consequences for the rate of cosmic expansion, the distribution of galaxies, the temperature of the microwave background, and the long-term fate of the observable universe. They ask us to reckon with the fact that the structure we see in the cosmos is defined as much by what is not there as by what is. And they ask us, perhaps most uncomfortably, to confront the possibility that our own cosmic address, our own location in the universe, is not at the center of density and richness, but in the relatively empty outskirts of the large-scale structure, living inside a void that may be quietly biasing our measurements of the expansion of the universe in ways we have only recently begun to quantify. This is what the void is, not a mistake in the data, not a region where the universe forgot to put anything, not a curiosity to be noted and set aside. The void is a fundamental feature of the cosmos, one of the most ancient and most enduring structures in the universe, built from the same quantum fluctuations that built everything else, shaped by the same gravity that built every galaxy we have ever seen, and governed by the same dark energy that will, in the end, make the entire universe a void. It is the universe's dominant feature by volume, its most powerful cosmological probe, its most ancient imprint, and its ultimate destination. And it is right there, in every survey, in every map, in every three-dimensional atlas of the cosmos that has ever been constructed. We just had to learn to see the nothing.